All right, take a look at section 8.6. All right, so last time in 8.5, we looked at a couple ways to prove triangles were similar. We looked at side, 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 angle, side, and using similar triangles to find distances, lengths, all kinds of stuff. All right, first theorem we're going to look at is 8.4. And as I said, I'm going to draw a picture of it. And I think the picture might be what's really helpful. Okay. But it says if you've got a line parallel to one side of a triangle, and it intersects or crosses the other two sides, it divides the sides proportionally. Okay, so here's a picture of that. All right, so you've got a line, TU, parallel to one of the sides of the triangle, in this case QS. If you have that, it automatically divides the other two sides proportionally. Okay, so TU is parallel to QS. Look where TU intersects. Here and there. So now we could say that RT over TQ is the same as RU over US. Okay, a little bit, still a proportion, but a little bit different than what we're used to. And that works no matter which side you pick for that segment to be parallel. So you do it like this. Drawing a side parallel like that. This over that would equal this over that. You could set that proportion up every time. As long as you got one side parallel to a segment like that. Okay, so any question on the picture with that proportion? Okay, what's kind of nice about the second theorem is it's the same as the one we just did, except we're going to reverse it. We're going to do the converse. All right? So the converse is going to say, if you draw a triangle, and you have a segment like that, and this side over this equals that over that, then it proves these sides are parallel. So in this case, we're going to start with the proportion, and it proves the side parallel, versus starting with the side parallel and then getting the proportion. Okay, so 8.5 is the converse of 8.4. I'll put that in parentheses under it. So if you draw in a line and it divides two sides of a triangle proportionally, then it's automatically parallel to the third side. Okay, and here's the picture. So if you draw in TU, and then RT over TQ is the same as RU over US, it proves TU and QS parallel, those segments. And why we want to show segments are parallel is because then we can use parallel lines cut by transversals, and we can show angles are congruent, triangles are similar, all kinds of things like that. Okay, so again, for me, I think the picture and then the statement down below, that's the clearest thing you can look at. If the description helps you, then feel free to copy that down. That's on page 498. Right, and that's half the theorems we're going to do today. Any questions on those two? Okay, we haven't done a proof in a while. I know you guys are kind of sad we haven't done a proof in a while, right? Luke, sad about that? No. So we are going to prove one of these four theorems. Okay, we're going to prove the easiest one, which is 8.4. It's pretty straightforward. That's going to be the only proof we do today. All right, so in theorem 8.4, you are given AD and BE are parallel. I want to prove that CB over BA equals CE over ED. Notice we're not even using sides that are in triangles anymore. CE, that's a triangle. But ED, it's part of a trapezoid. Okay? So is BA. Just the part BA, that's not a side in a triangle. That's in a trapezoid. All right, so we're still basing our theorems off triangles, but we're kind of extending it a little bit. All right, so a hint at how you want to do this. First thing is you want to prove that you've got similar triangles. Okay, that's our first step. It won't give us this proportion directly, but it'll give us like 75% of it. We're just going to have to do something after. Right. Looking at that, is there anything else that I could start to say to try to show that I have similar triangles? Everyone see the two triangles we want to prove similar in that picture? Okay, ACD, that's the big triangle, and BCE, that's the small triangle. So that's our goal. I don't think we're going to use side-side-side similarity because we don't know any sides. So we're going to have to do stuff with angles. And we'll say something in a second that we already know about one of the angles. Yep?
Angle B and angle E are congruent, and angle E and angle B are congruent, and they're also congruent.
Yep. So, Luke, since there's two angles right here for B, can you be a little more specific about which one?
Angle EBC. And
EBC. Okay, let me write that down. Angle EBC is the same as which one?
CEB.
These two are the same?
Yes. Or, I'm sorry, DAC.
Yeah, I think these two are the same. Good. DAC. Right, we got two parallel lines cut by a transversal. Corresponding angles are equal. Well, I'll write this as a statement reason proof. Angle DAC. Let me write it a little smaller. Statement. Alright, so that's our first statement. First reason. Does anybody remember the name of that? If we go back, this actually goes all the way back to chapter 3.
Isn't that like corresponding angles have...
It's actually just one more word, corresponding angles. One word after that. This is something that was given to us, we did not have to prove.
Angles postulate.
Postulate, yep. This was the corresponding angles postulate. Good. Step 2. Okay, I might have done this in step 1, but this is okay. Let's just say what was given. Angle C is congruent to angle C. I don't need to be more specific because near C, there is only one angle. It's not like if I say E, you're not sure which one. C, there's no choice. What's the reason for that? Angle C is congruent to itself. We've used this. That's reflexive. Okay, now once you've shown that two angles match up in the triangles, we've shown the triangles are similar. That's all you need. So let's write down the similar triangles. I'll start with the big one. ACD, triangle ACD is similar. How would you say the letters for the small triangle? ACD and BCE. Yep. Good. And the reason? That's angle-angle similarity. Okay, angle-angle similarity. Okay, any question on that? All right, now I want to set up our proportion. Okay, because we know that these two triangles are similar, their sides are proportional. Okay, let's focus on the sides we really need to. Okay, look at AD and look at BE. In the final answer, in the proportion they want you to prove, do you see AD in it anywhere?
No.
No. Do you see BE? Or EB? It'd be the same thing. Rose? No. All right. So we're probably not going to be doing anything with those two sides. Let's look and see if we see AC. All right. Or do we see sides that make up AC? Do we see like an AB and a BC? AB, BC, different order, but yep, we got that. Let's look. Do we see DC? Or do we see a DE or an EC anywhere? Well, DE, EC. All right. So we're going to be doing something with the two long sides, right? Because there's parts of those in the answer. All right, so let's set up a proportion. Let's compare the big side on top, AC, okay, to the smaller side that's on top, BC. Any question on that step? Right, let's do the same on the bottom. Compare big side on the bottom, okay, CD, over the small side on the bottom, CE. And you know what I'm going to do? I'm going to try to write my sides in the order that they have them. I did CE. So did they. What's the other one we used? Let's see. They did CB. I did BC. I'm going to switch it just so it's the same as what they did. Okay, and the reason for that? If you have similar triangles, corresponding sides are proportional. So with similar triangles, corresponding sides are proportional. All right. Now we're going to do the tricky part. Okay, look in the top of my proportion. I have AC. If you go up to the diagram, does anybody see a different way to write AC as a sum? AC would be equal to what plus what? And this is the whole key that's going to make the proof almost done at this point. Yep.
AB plus BC.
Right. AC is the same as AB plus BC. Okay. I'm going to ask if anybody remembers what that's called. It's one of the very first theorems, postulates we did. So it's AB plus BC. Now I'm going to write BC as CB. Okay, now let's do the same thing for CD. Okay, CD is really ED plus CE. Okay, or you could write it as, yeah, let's do it that way. ED plus CE. Does anybody remember what that's called? When you take a big thing and write it as a sum of two or three smaller things. We did it with angles too.
Side addition postulate?
Close. Think about what we added here. What are all these short things called? They're not lines, but they're... Yeah? Segments, yeah. Segment addition postulate. Goes all the way back to chapter 1. Okay, now from here, we're just going to do a little arithmetic to clean this up. We have a common denominator. Put each factor, or I'm sorry, each term in the numerator over the common denominator. So you get AB over CB, okay, plus CB over CB. Do the same thing here. ED over CE plus CE over CE. Okay. And if you look carefully at what you just did, some of these fractions are going to cancel out. Okay, and they're going to be turned into 1. Okay. So I'm just going to call that step simplify. You had a common denominator. I just wrote each factor over the common denominator. Step 7 is also going to be simplified. What do you get if you do CB divided by CB?
It's 1.
Divide two things that are the same, you get 1. How about CE over CE? 1. So now we get this plus 1 equals this plus 1. That's step 7. Again, what did you really do there? You just simplified your fraction. Divide two things that are the same, you get 1. I can cancel the 1 from each side. How would you, what property could you use to move this 1 to the other side? Think about what's the opposite of addition. Kira? Subtraction. If you minus 1 from each side, you get AB over CB equals ED over CE. And that's the subtraction property of equality. I'll write out the word so you don't think it's substitution. All right, so subtraction property of equality. Now we pretty much have it. Okay, let's go back up and look at what we were supposed to get compared to what we have. We wanted, all right, so I've got AB on top, CB on bottom. Well, they had that on the left-hand side flipped. Okay? I have ED on top, CE on the bottom. That's exactly what they have, except flipped. All right? You're allowed to flip each side of a proportion, and it's the same thing. Okay? Because it's not going to mess up the diagonals. Okay? Bottom line, AB and CE, those are on a diagonal. CB and ED, those are on a diagonal. Okay, so we've basically proven it. Let's just flip what's on each side. So we get CB over, and I'll write it as BA instead of AB. Okay, just the way they did it. I prefer, sometimes I use alphabetical order, but they didn't, so that's okay. And flip what's on that side. If we had been a little smarter about how we set this problem up originally, we could have avoided this flipping in the last step, and we could have ended up with an answer that was exactly what they had. Right? We just would have had to set our proportion up a little different to start, and we didn't. All right, so the reason for that, basically I flipped what was on each side. I don't think there's a theorem or rule for that, but let's just write down what we did. Flipped. Well, you know what? Even better. Took the reciprocal of each side. And we ended up with what they wanted. Okay, so it's a little tricky to prove, but you started out with proving your triangles are similar, then using a postulate from segment addition way back from the beginning of the year, and then just doing a little simplifying with common denominators. Same denominator and numerator simplifies to 1. Okay, so not too bad of a proof. All right, so that's a proof of theorem 8.4. Now we've proven it. We're not going to prove it again. We're just going to use it to figure out this problem. Okay, so it says in the diagram, AB is parallel to ED. If they're parallel, I like to mark it. Okay, just take the diagram, put the arrows on there right away so we don't forget. Okay, they also give me 3 lengths. If these numbers weren't labeled in the diagram, I'd label those as well. Okay, BD is 8, DC is 4, AE is 12. Find EC. Wait, anyone think they could tell me how to set up? In fact, I'll put up the theorem so you can see it. How could I set up my proportion here to solve for, we'll call the distance between C and E, X. Oh, Alyssa?
4 over x and 8 over 12.
Okay, that might work, but can you try to set it up? So in the theorem, it usually does like one side of one triangle and then the other segment that continues on from that. So like CB over BA and then CE over ED. I'm not saying that your way wouldn't work. I'm
So,
just,
CB,
okay, so 4 over
8,
8, yeah,
x over 12.
equals X over 12. Okay. I do it that way just so I remember. Now, how did you say to do it, Alyssa? Let's see if it would have come out the same.
4 over x and 8 over 12.
As long as 4 and 12 are on a diagonal, okay? As long as 8 and x are on a diagonal, that way would have worked fine. It just didn't follow the same pattern as our theorem. She just rearranged it a little bit. But that would have been fine. Okay, so we cross multiply. 4 times 12 gives me 48. Equals 8x. And Sarah, what's my last step to get x by itself? Good. Divide by 8. Divide by 8. And 48 divided by 8, James? 6. So x is 6.
Couldn't you just said that you know that 8 is double 4, so you could just divide it 12 by 2 and gotten 6 and have the next.
Yeah. Yep. The only time is if it's decimals, it might be harder to do that in your head. You'd have to use a calculator. But yep, proportions, a lot of times proportions is all about finding a pattern. Do you see a pattern from one to the other? It's perfect. Nope, that's really good.
I'm a smart cookie.
Okay, any question on how we got 6? All right. Now this one's a little different. They're giving you all the sides, and they're asking, is MN and GH parallel? If they're parallel, these sides are going to be what, in one word? If MN and GH are parallel, when we set up our fraction, the sides will be proportional. Yep. If they don't come out proportional, the sides are not parallel. Okay, as we saw in the last problem, many ways to set up your proportion. Let's try to do it. We pick one segment and continue on with that. Pick another segment and continue on with that one. So Olivia, what could I put on my left-hand side? You basically can start with any segment you want. There's no wrong way. You could say any one of those 4 numbers and it's not wrong.
56.
Mhm.
Oh, the 21.
Yep. So she did 56 over 21. I'm going to put a question mark here because we don't know. That's what we're finding. Okay. And Ian, what would go on the other side?
48 over 16.
Yeah. Just make sure when you set it up, you do it in the same order. Okay? Big over the small, big over the small. Okay? Looking at that, do people think these two fractions are going to come out the same? I mean, 16 into 48, that's easy to do. 16 goes into 48 3 times. Does 21 go into 56 3 times? No. It's close, but it's not quite. Okay, it's like 2.6 repeating. So is what's on the left and what's on the right, are they proportional? No. So the question, determine if Mn is parallel to GH. Not parallel. Okay, that was theorem 8.5. Okay, the converse of 8.4. So any question how I figured out those are not parallel? You might have set it up a different way. As long as 21 and 48 end up on a diagonal, and 56 and 16 end up on a diagonal. And you might have also done it, if you think the way Luke does, looking at a pattern, well, if you take 16 and triple it, you get 48. So if you take 21 and triple it, you should get 63. That's not 63, it's 56. So they're not proportional. Okay, let's look at our last two theorems. All right, you guys have been looking at two parallel lines or two lines cut by a transversal. Okay, I think you're ready to step it up. I think you guys you're big boys and girls now. We can look at three lines cut by two transversals. All right, so if you have three parallel lines and there's two transversals crossing them, it divides the segments or divides the transversals proportionally. All right, so let's let a picture really helps here. R, S, and T are parallel. Three parallel lines cut by two transversals, L and M. What we're saying is that UW over VX equals WY. I'm sorry. UW over WY equals VX over XZ. Kind of looks like what we did before. Kind of feels the same way a little bit, where you pick a segment over the segment next to it, pick a segment over the segment next to it. We're not gonna go through and prove this one though. Okay, but that's theorem 8.6. That's on page 499. Okay, and you could also set it up if you wanted. You could do WY over WU, ZX over XV. As long as somehow WY and VX are on a diagonal, and UW and XZ are on a diagonal. There's no converse to this. Okay, we're not going to do the converse. Any question on theorem 8.6? All right, so you've got to be given parallel lines to start. That's the key. If you don't have parallel lines to start, this doesn't work. Okay, and then theorem 8.7. All right, this one's a little different. Okay, it says if you draw a ray and it bisects an angle of a triangle. Okay, remember, bisect means to cut an angle in half. Then it divides the opposite side, the side that it's cutting into half, in segments proportional to the lengths of the other two sides. Okay, that's kind of a lot to think about. But it's a pretty simple diagram. So if you draw a ray, and that ray bisects an angle, so in this case angle ACD and BCD, they're exactly the same. Then it divides the opposite side, okay, we're looking at side AB, into segments that are proportional to the lengths of the other two sides. In this case, the other two sides are AC and CB. All right, so here's your proportion you could set up. AD over DB equals AC over BC. Or I said CA, AC, CA, same thing. All right. So draw an array. This segment over that segment equals that segment over that segment. And like any proportion, there's multiple ways to set it up. You just have to make sure that DB and CA, I'm sorry, DB and CA end up on a diagonal. Okay. And AD and CB, those end up on a diagonal as well. Okay, so if I was making a reference sheet for the test, I would just put this picture and then what's true below. Because the picture tells you exactly what to do. All right? If you get a problem on the test, you're just going to have to fill in 3 out of 4 of those numbers and solve for the 4th one. One of them will be x. All right, so we'll do, let's do an example of theorem, let's do 8.6, and then we'll do one for 8.7. All right, so in this diagram, they've given me a couple facts. Angles 1, 2, and 3 are all congruent. What does that mean? If angle 1, 2, and 3 are all congruent.
They're all parallel.
Yeah, PS, QT, and RU are all parallel. You could kind of think of that as an extended case of 2 lines cut by a transversal, except in this case it's 3 lines cut by a transversal. All the corresponding angles are equal. Okay, so they're all parallel. Now that we know they're parallel, we can use theorem 8.6. Okay, PQ is 9. QR, let's see, is 15. ST is 11. Find TU. Okay, anyone think they could set up my proportion to find x here? Luke?
9
Yep.
over 15.
Yep, so you did that segment over that segment equals
11
yep,
over x.
11 over x. Keep 9 and x on the diagonal, 15 and 11. There's many ways to set it up. So 9 times x is 9x. 11 times 15, let's see, 165. And Tanner, how do I get x by itself? Good. Divide by 9. Okay, you could get a decimal. You're not always guaranteed to get a nice answer. In this case, we get 18.3. I'll write it like this. 18.3 repeating. Or you could write 18 and 1/3. That'd be okay too. Any question on that? All right, so the whole key is figuring out these lines are parallel. If you can't do that, you can't use that theorem. All right. And let's see. These will be our last 2. All right, so example 5. It says in the diagram, CAD is the same as DAB. Okay, so we've got a angle bisector, AD. Use the side lengths to find DC. Let's call DC X. Okay, we don't know what it is, so we'll just call it X. Let's go back and look at that theorem, how we set it up. You take AD over DB. Let's start with that. So we just write down the 2 segments that the ray is bisect. That ray that bisects that angle, write down those 2 segments. Okay, Denver, what's CD? X. Now, what's DB? I want you to think about it in terms of X and the 14. Mm-hmm.
So I have x.
14 what?
Well, 14x. 14 plus x.
So think about, let's say the x was 2. What would you do with 2 and 14 to find the other one? If the total is 14 and this part was 2. Subtract it, right? That would give you 12, the other part. So in this case, we don't know it's 2. We know it's x. So dB is 14 minus x. Okay, that's the tricky part some people get stuck on. Okay, so we have x over 14 minus x. My suggestion, put that in parentheses, because whatever you have on the diagonal, you're going to do a distributive property. Okay? All right, let's look at the next part. So we've got AD over DB. Now do the side of the triangle that's touching the original segment you picked. Okay? So we did x. The side that's touching the x is 15. The 14 minus x, that's dB. What's the side touching that? It's 9 units long. And now you just have to solve it. That's it. That's your proportion. Okay. Be very careful you do the distributive property on that diagonal. So we've got 14 times 15, so 205, 210, minus 15x. Okay, next thing I do is add the 15x to each side. Selena, what's 9x plus 15x?
24.
Good, 24x. Okay, and Marquise, my last step to get x by itself.
Divide by 24.
Yep, perfect. Divide by 24. Okay, so you should get about 8.75. Okay, it seems easy as I'm going through it step by step, but when you have a problem like this on the test, sometimes it's hard to figure out which theorem to use because we have so many. Okay, we have probably over 10, 15 theorems this chapter. So first thing you really got to figure out is which theorem should I even be using? Okay. But a lot of times I'm going to set diagrams up for you, so I'm hoping the diagram gives you a hint. All right, and our last one. Okay, in the diagram it says KL is parallel to MN. Find the values of the variables. So we've got x and we've got y. Okay, anybody have any thoughts on a proportion I could set up to either find x or y? Let's start with it. Let's at least do x. Anybody see a theorem that might apply? Think back to this picture. Okay, maybe something, or maybe this picture. Right. We have two parallel lines, and you've got the segments, okay, on the sides. Look at what you've got right here, two parallel lines. And you've got those segments on the sides. Let's start with 9 over 13.5. Okay, so this one's going all the way back to one of the first theorems we did. What would go in the top on the other side?
37.5.
All right, so I had 9 over 13.5.
Over 37.6.
37.5 is the whole thing.
Over x.
So I had this part over this part. I want this part over that part.
Oh!
Yep. Good, minus x. And then The bottom part is just x. Okay, so cross multiply. Okay, we've had a lot of 9x today, but it doesn't always happen that way. And I'll leave the rest for you to finish from there. So you cross multiply, solve for x. I'll tell you what you should get. X should be, let's see, 22.5. Okay, so try to finish that up. I think you'll get 22.5 very easily. All right, so the homework is on 502. Okay, I'd like you to try 11 to 18 all, 21 to 28 all, and 31 and 39.